Hello, this is Mr. Collier, and today we're going to look at the Fibonacci sequence and figure out a formula for finding the nth term. So if you look at the Fibonacci sequence, you get each term by adding the previous two terms. For example, you get 8 by adding 3 plus 5, and you get 13 by 5 plus 8 equals 13. But what if you wanted, let's say, the 100th term? If you wanted the 100th term, doing it this way, you'd have to add the previous two terms together 100 times in order to get the 100th term, and that would take a long time. So it would be a lot easier if we had a formula that you could just plug in a number and get the 100th term by just using a formula. So that's what we're going to do today. We're going to find a non-recursive formula for the Fibonacci sequence. Okay, so we're going to do it using this theorem about homogeneous second-order linear recurrence relations. So if you want to figure out how to use this kind of thing, I have some examples on YouTube already of how to use this theorem to find equations for recursive relations. Okay, so we're going to use this to find a formula for the nth term of the Fibonacci sequence. So we're going to use this part right here, a sub n equals this expression here, and we're going to use that to find the equation. Okay, so if we look at this, we can write this relation as a sub n equals a sub n minus 1 plus a sub n minus 2. You add the previous two terms. This is how you write it. Okay, so solving, you get a sub n minus a sub n minus 1 minus a sub n minus 2 equals 0. So the characteristic polynomial equation is x squared minus x minus 1 equals 0. This can't be factored, so you have to use the quadratic equation. You get x equals negative b plus or minus root b squared minus 4ac out of 2a. And if you do that, you'll get two solutions. X1 equals 1 plus root 5 out of 2, and 1 plus root, 1 minus root 5 out of 2. And some of you may notice this is actually phi, which is the golden ratio, which is approximately 1.618, and so forth. Okay, so this phi pops up because in order to find the golden ratio, you use the same quadratic equation to find this number. So it's not really a coincidence there. All right, so we have our solutions. That's x1 equals this, and this is x2 over here. We have our two solutions to the characteristic polynomial equation. So we're going to use our formula now. We're going to use this one here to find the equation. So we have a sub n equals c1 x1 to the power of n plus c2 x2 to the power of n. And of course we have x1 is 1 plus root 5 out of 2 to the power of n plus c2 times our x is going to be 1 minus root 5 out of 2 to the power of n. Okay? Now, our initial conditions are, well, in a Fibonacci sequence, your first two terms are 1 and 1. So a naught is equal to 1. Okay, the first term is equal to 1, so that should be equal to, now, 1 plus root 5 out of 2 to the power of 1 is just 1, and this to the power of 1 is, or 0 is just 1. So we have 1 equals c1 plus c2. Okay, and if we look at our second initial condition, a1 is also equal to 1. So that equals c1 times 1 plus root 5 out of 2 to the power of 1 plus c2 times 1 minus root 5 out of 2 to the power of 1. Okay, so now we have to find c1 and c2, we have to solve this system of equations. So it's going to be pretty tough. It's going to take a lot of steps and a lot of complicated algebra and surds and such, but we're going to get this done. So if you look at this equation here, this means that C1 equals 1 minus C2. So we're going to substitute that in right here. Okay, so we have, first of all, okay, let's do that. We have 1 equals 1 minus C2 times 1 plus root 5 out of 2 plus C2 times 1 minus root 5 out of 2. And to get rid of the fractions, I'm going to multiply everything by 2. And I get 2 equals 1 minus C2 times 1 plus root 5. I just like to do this because I think it's a bit easier. So we have this equation. We're a bit closer. Now we're going to multiply everything out, expand the brackets. 2 equals 1 plus root 5 minus C2 minus C2 root 5 plus C2 minus C2 root 5. Okay, hopefully we'll get some stuff to cancel here now and make this a bit simpler. We have a minus C2 and a plus C2 cancel. And what's next? So we have, let's bring our constants to this side. So we can subtract 1, we'll get 1. Subtract root 5 from both sides, we get 1 minus root 5. On the other side, we've got negative C2 root 5, negative C2 root 5, so that's negative 2 C2 root 5. Okay, and solving for C2, we can divide by negative 2 root 5. So we're going to have 1 minus root 5 out of negative 2 root 5 equals C2. And we're going to substitute this into our original equation in a second. So it would be easier if this looked like what we had before. So it would be easier if I rewrote this as C2 equals negative 1 over root 5 times 1 minus root 5 out of 2. Okay, I just rewrote that, and now that looks like what we had before, so that's going to make simplifying a bit easier. So this is very important. This is what C2 is equal to. Now we're going to find C1. And recall that C1 equals, I believe, 1 minus C2. Okay, which equals 1 minus, and here's C2, negative 1 over root 5 times 1 minus root 5 out of 2. Okay, so there we have it. So what's going to happen here? We're going to have, alright, so let's work that out. So we're going to have 1 plus 1 minus root 5 out of 2 root 5. To add that together, we're going to take 2 root 5 out of 2 root 5, which is equal to 1, plus 1 plus root 5 out of 2 root 5, which equals, actually I made a small error, that's 1 minus root 5, so let me fix that. Okay, so when I add this together, I'm going to have 2 root 5 plus 1 minus root 5 out of 2 root 5. Okay, and when we do that, we get 1 plus root 5 out of 2 root 5. And let's factor out that root 5 so we can, so it looks like what our surds look like in the original equation. So it looks like this if I factor out that root 5 in the denominator. Oops. Okay, so that's the value of C1. And we have C2 from before, and then we're going to write our equation now and then simplify. So a sub n equals, remember it's C1 x1 to the power of n plus C2 x2 to the power of n. C1 is right here, 1 over root 5 times 1 plus root 5 out of 2. Okay, times x1 to the power of n. If we look back at the beginning, x1 is also 1 plus root 5 out of 2. That's to the power of n. And C2 is the same as this, except there's a negative sign. You can see that from before. It's right there, right here. So we're just going to put that in, substitute that in. So that's negative. It's going to be negative 1 out of root 5 times 1 minus root 5 out of 2. And x2 is also 1 minus root 5 out of 2, but that's to the power of n. So we can simplify now, because we've got this here to the power of 1. This is also to the power of n. We're going to have 1 over root 5 times 1 plus 1 plus root 5 out of 2 to the power of n plus 1. Just add together the exponents here. And 1 over root 5 times 1 minus root 5 to the power of 2 out of 1, oh, sorry, my bad. We're adding together those exponents. So you get n to the power of, or to the power of n plus 1 here. Okay, so that is a formula for finding any term in the Fibonacci sequence. Okay, so remember the Fibonacci sequence goes 1, 1, 2, 3, 5, 8, 13, 21, and so forth. I've done this on the calculator already. Let me bring this in here. So I've typed this on the calculator. I'll use 6 as the exponent here. That means I'm finding the 5th term, and I got 8 for the 5th term, and that is indeed 8 for the 5th term. Remember the terms go 0th, 1st, 2nd, 3rd, 4th. So our 5th term is 8. Remember at the beginning we want to find what the 100th term is. Let's find the 100th term now. So you would use to the power of 101 to find a 100th term. Let's see if our calculator can do that. That might be a bit too big. Let's see. Oops. So I'm going to change this number to 101. And let's see what happens. And I also need to change this number to 101. I need to insert 101 and delete that 6. Oops. What did I do right there? I need to insert the minus. Let's see what happens. Oh, so we get a very large number for the 100th term. But you can see that our formula works. And now you can use the formula to find any term in the Fibonacci sequence without having to write out the entire sequence.